So for the next part, our Thai team will show you the video presentation of our software. But before that, let me introduce myself a little bit. So my name is Kris Prasopsanti. I am a process engineer at PSE for Speed. Um, I have background in both chemical and engineer and computer engineering. And right now, most of my work are about process design, improvement, as well as the computational modeling method. And for the first video we will show you is about the demo of the education mode section of the Hybrid-AI-sep, which will behave like the chatbot for the chemical and separation problem. So in the video, it will show you how it works as well as how it connects to other part of our tool. So let's start the video.
Now let's start the demo section. The first part I will show you is the educational mode. This mode is meant for students, trainees, or practicing engineers who want a quick and reliable way to review fundamental concepts in separation processes. The answers you will see here do not come from open-ended language generation, but from a structured knowledge base built specifically for this domain. That means the explanations are consistent and technically accurate, while still keeping the flexibility of a chat interface. As we go through, I will ask the system a few example questions, such as, what is an azeotrope, or how do you separate azeotropic mixtures? We will look not only at the main explanations, but also at the additional features, like related terms, suggestions, and resource links, that make the answers more useful. Let's begin by looking at the interface. First, let's take a look at the interface of the educational chat mode. At first glance, it looks like what you would expect from any chatbot interface. On the left, you have the menu where you can switch between different modes. For now, we are focusing on the educational mode. In the center, you have the main chat area, where the responses will appear once we ask questions. At the bottom, you can see the familiar input box where you can type your question, and a send button to submit it. This design is intentional. We want the interface to feel natural, like using ChatGPT or other chat systems, so users can focus on the content rather than learning a new way to interact. Now, let's begin with broad, conceptual questions, starting with, what is a chemical? Here the key point is not just the definition itself, but where it comes from. Instead of relying on broad internet data that may or may not be reliable, every response is pulled directly from a validated, domain-specific knowledge base. This ensures accuracy, consistency, and alignment with the terminology actually used in chemical engineering practice. The responses are concise, like what you'd expect from a general LLM, but grounded in curated technical sources. For example, mole fraction is explained in terms of its role in thermodynamics and equilibrium, while mixture is linked to phase behavior, state, and type. At the bottom, related terms appear automatically. These are not filler keywords, they act as links in the educational flow. Here, chemical leads into mole fraction, then into mixture, and naturally into azeotrope, which becomes our first major technical concept to be highlighted in the next slide. Here we reach our first major technical concept, what is azeotrope? The system defines it as a mixture where vapor and liquid phases have the same composition at a certain temperature and pressure. It distinguishes between homogeneous azeotropes, like ethanol, water, and heterogeneous azeotropes, where more than one liquid phase is present, that is, the liquid in equilibrium with the vapor phase splits into two liquid phases, for example, water plus 1-butanol binary mixture. What makes azeotropes important is their role in chemical engineering practice. Because they behave like a single substance at the azeotrope point, they cannot be separated by ordinary distillation into two pure products. That is why they are both a challenge and an opportunity in process design. This is also where the program begins to shift. Instead of just giving general knowledge, it is now tying concepts directly to engineering relevance. Compared to the earlier broad definitions like chemical or mixture, you will notice that here we also get an additional information section. These are not links to external websites, but references into the system's own structured knowledge base. For example, here we see entries like theory of azeotropic mixture, high boiling azeotrope, or low boiling azeotrope. These point to internally validated teaching modules, so users can explore more details while staying inside the same search environment. This feature does not show up for every question, only when the concept is technical enough that extra theory or worked out references are relevant. That way, the interface stays focused but still provides depth when you need it. The additional information links we saw earlier can also be accessed from the Knowledge Files library. The Knowledge File library contains short presentations on selected topics in the form of videos or PDF files. This way, users can look up the same materials directly whenever they need them. Here is an example of explanations related to residue curve maps on ternary diagrams. This is a more advanced topic. Interpreting ternary azeotropes and residue curve maps can be quite challenging, and without guidance, it is easy to make wrong conclusions. Let me briefly explain the contents on the theory. At the top, 3 ternary system residue curve maps are shown. The first ternary on the left represents a binary azeotropic mixture with a solvent. The second ternary system shows a system with 2 binary azeotropes. The third ternary system shows a system with 3 binary azeotropes and 1 ternary azeotrope. The text in the bottom left represents the model equations needed for computing bubble points. The text in the middle shows the computational steps needed to generate a ternary residue curve map. Having the explanations available here helps users to approach such topics with the right level of explanation and supporting references. Now that we have seen how the background materials and video support learning, let's return to the main educational flow. Alongside the main explanation and additional references, the system also offers suggestions and direct links to other tools in the hybrid AI environment. This is where educational mode connects seamlessly with other options available in the software. For example, instead of stopping at the definition of azeotrope, you can immediately move into browsing azeotrope data or testing mixtures in the VLE calculator. What the software allows is to let users pivot directly from reading about a concept into applying it. You can start from a definition, then with one click move into simulations, data lookup, or design workflows. It keeps the experience consistent. You begin with context and theory, and you're guided smoothly into practice inside the same environment. Let's look at another example. When we ask the software about azeotrope separation, it explains why these mixtures are challenging. At an azeotrope, the vapor and liquid compositions are the same, so conventional distillation cannot drive separation beyond this point. That is why conventional distillation, even with very high number of plates or reflux, becomes ineffective. To address this, the system points to advanced methods such as adding an entrainer in extractive or azeotropic distillation, using pressure swing distillation when azeotropes are pressure sensitive, or applying liquid extraction through an appropriate solvent. This explanation gives a clear baseline. Conventional distillation cannot be used to separate azeotropic mixtures and requires targeted strategies. But the real strength of the platform lies in what it adds on top of this: structured resources, additional theory, and integrated tools for separation techniques. Compared to the azeotrope overview, here the software does not just add more references, it also introduces a broader set of integrated tools, functional modules you can launch directly. These include resources like the azeotrope database for browsing compositions of known azeotropic mixtures, as well as unit simulators for methods such as liquid extraction or pressure swing distillation. At a higher level, the process design mode can be integrated with the computer-aided flowsheet design software, ProCAFD, to offer fully integrated process design workflows. We will return to some of these topics in the next sections, when we move into an example for separation process design. But for now, let's go a step further and look at solvent-based extractive distillation, one of the key methods used to separate azeotropes. The software defines it in the classical way: a high-boiling, non-volatile solvent is introduced above the primary feed, remaining concentrated in the liquid phase and altering relative volatilities without forming new azeotropes, and extracting one of the compounds of the binary azeotropic mixture. The typical solvent-based extraction process flowsheet has 2 columns, the extraction column and the solvent recovery column. with the solvent recycled from the recovery column to the extraction column. And again here, the software recommend the user either to test solvent-based extractive distillation directly in the simulator, or to continue by selecting one of several available options under problem solution. That second path is what we will follow, because it gives us the complete process view, connecting unit simulators into a structured workflow. This tool is also the same one you saw labeled as chat problem solution mode in the left-hand interface. So this creates a natural transition. We have moved from definitions in educational mode into applied process design. And in the next section, we'll demonstrate the Hybrid-AI-sep by working through the problem solution option for an acetone chloroform separation problem.
Okay, so